Ranking every item is impossible once the catalog gets large. TensorFlow Recommenders trains separate query and candidate towers. Then ScaNN retrieves a shortlist you can actually rank. You'll see how to connect the pieces into a workflow that learns matching towers and returns a shortlist for ranking. I'm Professor Pi, teaching search and IR with simple Python. Large catalogs break naive scoring. If you try to score every item at request time, latency explodes and models get expensive. Two-tower retrieval solves that by learning compact embeddings for queries and items, so a fast nearest neighbor search can find a small candidate set to rank. TensorFlow Recommenders pairs nicely with ScaNN for the fast index, so you get a trainable matching model plus a production-friendly search layer. At a high level, you want the system to learn which items belong together from clicks or plays. Then use that learning to reduce millions of items to a few dozen candidates. The towers learn embeddings aligned for similarity, and the index lets you retrieve nearest neighbors quickly. The risk to watch is recall. If the index returns the wrong shortlist, the ranker never sees the right item. We will build a minimal pipeline that demonstrates the full loop. First, we create a tiny implicit feedback dataset that teaches the model what belongs together. Then we build query and item towers that embed IDs, train retrieval with TensorFlow Recommenders, measure retrieval accuracy with FactorizedTopK, and finally export a ScaNN index for serving. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by creating the compact dataset that will drive training. This snippet creates the smallest useful implicit feedback dataset for retrieval, so the model has a real signal to learn from. Clicks holds query positive candidate pairs, and items is the catalog the retrieval layer will search later. We import TensorFlow Recommenders as TFRS for the retrieval APIs and use TF-data dataset from tensor slices to keep the data pipeline consistent with larger setups. The printed output simply shows how many positive pairs are available for training. With those pairs in hand, we need towers that turn IDs into compatible vectors for fast search. This example turns raw IDs into comparable dense vectors by putting the query and candidate sides into the same embedding space. Query tower maps user ID values, and item tower maps item ID values. Both use string lookup followed by embedding, so the outputs are dense vectors we can compare. The .style score is just a sanity check at this point. Untrained, it only confirms the towers produce compatible shapes and some numeric affinity. The output shows an initial match score we can improve with training. The towers give vectors, but they must learn from clicks, so affinities reflect real behavior. This code trains the two towers with TensorFlow Recommenders, so they actually learn useful embeddings from the interaction data. The model keeps query tower and item tower separate, which is the key trade-off that lets us pre-compute candidate embeddings while embedding the query at request time. Compute loss plugs matching rows into TFRS.tasks.retrieval, which treats other batch items as negatives for this compact example. Compute metrics false keeps the loop focused on loss, so training is lighter. We save the heavier catalog metric for the next step. The final printed value is the training loss, showing the towers adjusted to the positives. Now we need to answer a practical question. Does training actually make the index useful for recall? This snippet checks whether the trained towers can recover positives from the catalog, which is what matters for downstream ranking. TFRS metrics FactorizedTopK embeds the candidate catalog with item tower. Then update state compares each query embedding against the true clicked item embedding. we request cutoffs with ks equals 1, 2, and read the top 2 result with metric.result. The output is the top 2 accuracy, the retrieval stage signal that tells you whether the candidate set is worth handing to a ranker. When the recall looks reasonable, package the retrieval step as a fast index for serving. This example packages retrieval as an exportable TensorFlow Recommenders ScaNN index, so you can run fast nearest neighbor lookups in production. Index from dataset stores catalog IDs next to embeddings produced by item tower, and tf.savedModel.save exports a callable index. After tf.savedModel load, the loaded model accepts a raw query ID because query tower was attached to ScaNN. Increasing k returns a larger shortlist for downstream ranking. Decreasing it saves work, but raises the recall risk. The output shows the first retrieved candidate from the saved index. This toy flow maps directly to product use. You would pre-compute item embeddings on a schedule, host the ScaNN index in a low latency service, compute the query embedding at request time, and hand the top candidates to a heavier neural ranker or a re-ranking policy. 3 quick takeaways. Train separate query and item towers so you can pre-compute candidates and serve fast. Use 2-tower retrieval when catalog size or latency rules out scoring every item. And watch recall. A tighter index saves work, but can drop the right item. Tweak one thing next. Increase the ScaNN K parameter to return more candidates. Then measure top K recall with FactorizedTopK to find the trade-off that suits your ranker. If you want practical IR recipes like this, subscribe and watch the IR videos.